I got the calendar up here for the 120, just so you can see what we're up to in regards to time. So we've got to be ready for the midterm in a little less than 2 weeks. So it won't. I'm going to be going over these in 120 portion, 10.1 through 10.3. It's not as much as it looks like. Probably, yeah, I could almost go over this in one night, but I'm going to try to break it up between now and Tuesday, and then next Thursday we'll be reviewing for that midterm, and then the midterm on the 5th. Okay, and
Question,
remember that's got to be on Respondus.
Mr. Cruz, that
Mm-hmm.
10-1 chapter, it's gonna be on there, or we just
Yeah, everything. See here, 2, 3, 10.1 to 10.3. The reason being is
so
chapter
test
10. Chapter 10 is rather long. See, it's got 8 sections in it. So since the 10.1 through 10.3 is not too bad, we'll do that first, and then we'll come back to the rest of chapter 10 after the midterm, and then we'll test on that section. I mean that section of the chapter, and it'll make it a little bit less taxing, I think, to break it up like that.
so we're gonna have test 1, 2, and 3 gonna be on midterms.
Chapters, yeah, chapter 2, chapter 3, and then the first 3 sections of chapter 10.
All right.
Okay, does that make sense? Or at least
Yeah, so you saying you're gonna
then
stop at 10-3?
before the midterm, yeah.
Okay.
All right. So what I'm going to do tonight in the O2O is I'm going to just kind of give you a little tour of 10.1, and then in the 120 hour we'll cover as much as we can, attempt that the 3 sections kind of more formally, and then I'm going to have a little it's a little evaluation. It'll be open, and there's a couple of questions in there that's from 10.1. So you might want to wait until we finish. You got several, chances on it. It's just to give us a participation grade in the O2O. Okay, so that's not the coin flip I wanted. Rather than kind of doing it with a real coin, which is really hard to do on here, there's a nice little tool over here to simulate it. And I can just show you a few things to kind of have some ideas here. All right. So first of all, probability is just the study of how likely something is to happen. Probability is a way to quantify. In other words, we're going to give a number that's going to tell us from looking at it whether something's a good bet to happen or not. All right. Now we use the word of experiment should just denote any kind of an operation that we know generally what will happen, but we don't know specifically what will happen. In other words, if we roll a die, we know from this here, you see that's the sample space, what we call it, the head and the tail. There's 2 sides of a coin. That is going to be one of those. it'll be a head or a tail, but we don't know which one. So if we want to find the probability of a head or the probability of a tail, we can do calculation to find that. Same thing with this down here with the die. On a die, there's 6 sides. Now, that's not 6 dies. That's just letting you see all 6 sides at once because, of course, a die is a cube and it has 6 sides. And there's a 1, a 2, a 3, a 4, 5, and a 6. All right? An event is just a subset. In other words, you remember we talked about subsets in chapter 2? Of the outcomes of experiments. So event refers to one subset of the whole set. So to kind of break it into terms of, let's call C, set C. So this is what we're looking at. So the coin, we'll just call it C for coin. It has 2 sides on it. All right. So let's call another one just T for tails. Okay. So they look like sets now. To find the probability of a tail, we put the number of elements in T over the number of elements in C. So in other words, the probability of a tail, and we just use the P to denote probability so we don't have to write it out. You know, people in math are real big on using shorthand. So the probability of T is equal to 1 over 2, which is 1/2. And that kind of makes sense, which that's 0.05 if you do it as a decimal. See if we can get the calculator out here and show you. So I'm going to take 1 and divide it by 2 and see we get the 0.5. So fraction-wise, 1/2 is the probability of getting a tail when we flip a coin, which is 0.5 decimal-wise. You have to watch things in ALEKS because sometimes they'll say a simplified fraction, and then sometimes they'll say a decimal rounded to a certain place. Now, how would we write this as a percent? How would we do that? What would that be?
Do you move the decimal 2 places to the right?
Yeah, great. Nick, watch that. So what we do is we go 1, and then we go 2, and then we fill in there. So that's equal to, and I'll do it with the text thing because it'll look nicer. %. And if you think about that a minute, that should make sense because 1/2 of anything, 1/2 of a pi is 0.5%, 0.5 decimal wise, and 50%. Okay. So there's going to be a little in one of the in that little evaluation, you're going to have some of these conversion things, and that's important because in chapter 10, not so much in the before midterm, but afterwards, there's going to be times when you've got a percent and you have to convert it to a decimal to proceed with calculations, and then convert back to a percent. So we got to make sure we understand how this works about going back and forth. And then to get a fraction into a decimal, you divide numerator by denominator. All right. So those are just the basic little things that we kind of need to know for the 120 thing. All right. So let's see. Let's see if I can put this in here in text, and I'll just kind of go back and forth. So 1/2 is equal to 0.5, and you can put in the extra 0 there, and that maybe makes it easier to see where the 2 decimal places are. But you don't need to write it there for 0.5 because there's nothing in that hundredths position. It's a 0. So this is what we got. And so to go to percent, you go over 2 to the right and add the percent sign. To go from percent back to decimal, you go 2 to the left, 2 to the left. To go from decimal to percent, 2 to the right. So let me write that out. Okay. To convert percent to decimal, we shift 2 places to the left. Okay. And I know it can be a little bit confusing because of the fact that, why do we need both? Well, I'll just explain my take on why we have percents. Percents have been around a long time. And the percents, for some reason, people have a more natural ability to understand percents than they do decimals. For example, our money is like a dollar is 100 cents. So if we have 50 cents, 0.5, like this right here, that's 50% of a dollar, or 50 cents. So you're kind of doing the same thing when you're talking about money. It's just you don't think about it, but this is what you're doing. All right, any questions? All right, let's see what else we can do. Now, as I said, an event is a subcollection or a subset of the outcomes of an experiment. Now, did I see? Just to let you know, the sample space, I don't know if I specifically read out this, but the sample space, when you see that term, it just means that's all possible outcomes you can have from doing that experiment, like the heads or the tails. There's 2 of them. There's 2 of them. So that's our sample space. For the die, there's 6 sides. That's our sample space. Okay. So Alex uses that term a lot. So that just means all possible outcomes. So this right here is the sample space for a coin flip. And then this right here is the event for a tail. And it's like I said, it almost seems kind of trivial. I know there's some questions in Alex. It'll be something like they'll give you a set of things, sort of like this, and then they'll say, write out the sample space for it. It's basically just repeating it verbatim. It's not asking for anything elaborate, because the sample space is just all possible outcomes. And the event is just the possible outcomes for whatever we're talking about. In the case of a coin, there's just one of them for a tail. All right. Let's talk about it within a different context. Let's so this right here, I got it handwritten out just because I wanted it to look kind of informal. But the way you calculate any probability, and sometimes the term theoretical, empirical are used, and the only thing that's different between theoretical and empirical is just that theoretical kind of exists by nature, and empirical is just from observed data. I'll show you what I mean in a bit. And we just looked at the coin, but let's talk about an odd number on a die. When it's just one die, it's called a die. So we already looked up here that the sample space has 6 elements in it. So let's go and put in a little part right here. Well, let me do it on the annotation. And if you got any questions, just speak out. All right. So the sample space, and we'll just say D is 1, 2, 3, 4, 5, and 6. And I'll just put here sample space. Okay. Now, let's say we want to find the event for odd. Let's call it O. The odd ones are 1, 3, and 5. Okay, so this is the event for rolling an odd number on a die. So then what we're going to have is, and I'm going to have to write it out because it can't do fractions with text too well. So the probability of odd, we'll just call it, do it like this. All right, the number of elements in, remember that terminology from chapter 2, the N of, we went over that for a reason because we're going to use it here. Make a little line there. Okay, there we go. So how many elements are there in O? Right here.
3.
How many elements? Yeah, 3. Good. So let's see if I can write out a 3. And how many elements are there in D? Hey, there's a hint right there. That should be easy because what's the last number? How many numbers are there? 1, 2, 3, 4, 5, and 6. The large number always is going to go on the bottom because we're going to see in a minute, a probability is always a fraction. When I say it's a fraction, it means it's going to be between 0 and 1. It doesn't have to be expressed as a fraction. It can be expressed as a decimal, as we saw up here with the one up here. Okay, it can be expressed both ways. And if we keep it as a fraction, because sometimes Alex will ask for it as a simplified fraction, so we need to make sure we know how to simplify fractions. So 3 goes into 6 twice and into itself once. So then the simplified probability is 1/2. So odd on a die, the probability is also 1/2 because exactly half of the die numbers are odd. And that's also could be written as 0.5. Watch what Alex asked you to write them in, because if it says simplified fractions, that means you got to do this kind of thing here. 3, 6, it's probably tell you something like, oh, although your answer is right, it's not simplified. At least in the path it will. When you get over to the quizzes and the tests and such, they may not do that. All right. Let's see. Now, equally likely outcomes just means that something has the same. I'm going to take this and put this down in here at the bottom of this. Okay, so probabilities have certain properties. I'm going to come back and show you that little video in a minute, because it'll be nice to help you get through some things or understand what's going on. It doesn't really, there's nothing really in it that you're tested on, but it helps with understanding. All right, so here's some properties of probabilities. Probabilities have to, first of all, they can't be any less than 0. And 0, if a probability is 0, which is the lowest it can be, then it means that that event cannot occur or will not occur. All right, that's property number 1. Second, the probability of an event will occur is 1. So if something will happen, the probability is 1. Now, that being said, that's the 2 endpoints. The probability is always going to be between those. And that's why I had said it earlier, the probability is always a fraction. Now, it doesn't have to be written as a fraction. It can be written as a decimal, but the probability always has to be within 0 and 1. It can never be negative, never greater than 1. That's why what we did over there when we did that, when I did this one with the writing it out, wherever it was at. Like right here. The small numbers on the top. So whenever you have, if you put the 6 up on top and the 3 at the bottom, then you got 2. So that should be a hint that something's wrong. Okay, the large number always goes in the denominator. See, and this little formula also kind of clears that up for us, because what it does is it tells us the count of all possible outcomes is on the denominator. The big number is on the denominator. Since the event is a subset, then the most it can be is the same as the denominator. It can never be greater, because if it's greater, you got a value greater than 1. In theory, if you got a probability that comes out to, let's say, 8/8, that would simplify down to 1. And that's the greatest it could ever be. All right. So let's check off 1 and that one. And then when I move up, those are going to go away. Let's see if I can borrow some room here. I guess there is a way to do it. That won't work. Okay. So now this is just a little breakdown of how it looks. Impossible being 0, certain being 1, and then in the middle, this is what people like to call 50-50, the 0.5, which we just calculated. And so that means that it's kind of a coin toss, and that might be the way that we've seen it. When we say 50-50, it means that there's an equal chance of something happening as well as not happening. And as we get closer in this direction, things get more and more unlikely. On this direction, things become more likely. Okay, and then until we get up to 1. Now, the sum of all probabilities for a given experiment will add up to 1. Now, what does that mean? Well, remember on our die situation up there, on our die, there's 6 sides of that denominator. I'm sorry, 6 sides of that die, a die that will be in our denominator. For any one of the calculations of any kind of a scenario in there, we saw it for odd, that the 6 is in the denominator, and then the 3 ones that are odd in the top. But let's just look at each one of the numbers here. If we want to find the probability of a 1, well, how many 1s are on that die? There's only 1 1. Likewise, there's only 1 2. There's 1 3, 1 4, 1 5, and 1 6. Okay. So being said, look at this right here. Okay, so the probability of a 1 is 1 for the 1 1 over 6. The probability of a 2 is 1 over 6. The probability of a 3 is also 1 over 6. The probability of 4 is also 1 over 6. The probability of 5 is 1 over 6. And probability of 6 is 1 over 6. Now, again, this is not something that you might see this term, but you don't really have to know it, other than if you see it, kind of know what it means. And what equally likely outcomes means this: for that die, each one of the numbers has the same chance of occurring. And as I had said here, the sum of all probabilities of a given experiment is 1. So if we have a pie that's cut into 6 pieces, then all 6 of those add up to be 1 pie. So that's what I'm showing here. 1 6 plus 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 1 6 in the numerator. Since it's got the same denominator, we keep the 6 for the denominator, add up all the ones, and that's 6 over 6. Any number divided by itself is 1. So that's how equally likely, well, that's what this is talking about here. And it's real easy to see. when you're talking about these equally likely outcomes, because sometimes they may not be for probabilities, particularly for an empirical problem, which is what this is. In empirical, don't let the word throw you like it's something different. You still calculate probability the same way with small number in the numerator for the number in your event, and then the denominator is just the number of elements in your sample space, which is the denominator. Okay, and there was one more thing here. This complement rule, and this is really the same complement rule from back in chapter 2. But the way it works is, and I probably ought to kind of write that out, because see how it says the up here where we said the sum of all probabilities of any given experiment is 1. So that would be like this: probability of A plus the probability of not A. And that means the same thing as the complement. Remember over in chapter 2, it was like a little apostrophe. These add up to be 1. You can kind of see this in the concept of like weather. If you watch the news, or if you look at a weather site, if you look at the weather, or you look at a weather site, if you're told that it's 70% chance of rain, then 70 from 100 leaves you with 30% that it will not rain. And that's the complement rule in action. That's what this is right here. But it's more useful if you write it like this. Oh, I'll tell you what. I can fix it. I'm going to do something else here. That was already written. I just wrote it up there, so I'm going to. I'm not going to belabor you about why this is true, but basically it's algebra. This is the one thing where algebra is used, but you don't really need to do this if you understand that this is the way the complement works. Because the two things add up to be 1, if you subtract one of these from one side, you subtract it from the other to keep it balanced. And so if we subtract this part to get rid of it there, it goes on the right-hand side and it becomes negative, and therefore we have this complement rule. And then the flip side of it is, well, if we solve for this part by getting rid of that, by subtracting, then that would be 1 minus PA. So there's two manifestations of it. And in the 120 ALEKS, there are some problems where they ask you to use that. All you're basically doing is you're just, like, for example, they're giving you this and they want to know this. All right, but let's do a little probability problem here. This, again, this is what we call empirical data because it's something that's being collected. As it said, on the coin or on the die, those things are essentially, they're just built in. The die's got 6 sides. You roll it, and we know what the probability of each one of those are. And that doesn't mean we can predict what's going to happen, and I'll show you in a second. Let's go ahead and just do this using basic probability. Okay. So it says from the given chart here, this is a chart for showing the results of a blood drive. And at that blood drive, there were 500 people that gave blood, and 223 were type A, 51 type B, 16 AB, that's the rare one, and 210 is O. And they all add up to 500. So let's gonna look. All right, so the first thing we want to find the probability of AB. Okay. So let's do it with this. I've already done it down there, but I want to do it so we can kind of see a little bit better. So what we're going to do is in the denominator, we're going to have 500 because that's the total number in our set. All right. And how many is AB? It's 16. Now, if we divide both of these by 4, then that's the simplified fraction. So let's go ahead and do the fraction. Now, if you rusty on converting to, are y'all hearing me okay? Hello, hello.
Yeah.
Yeah, we can hear
We
you.
hear you, we hear you.
All right, y'all just quiet.
We're
Yeah, we
just
can
trying
hear
to
you.
concentrate on what you're
Okay,
teaching us.
all right. So now, if we want to put that to a decimal, then we're going to take the numerator and divide it by the denominator, and that's going to give us this value here. All right. Okay. And you can see I'd already done that at one time. All right. How about O? The probability of O. Probability of O is equal to same kind of thing, the same denominator. When you're dealing with the same experiment, which is what this is, the sample space, the denominator is going to say the same. What's going to change now is the numerator. Now we're going to put up here the number of O people. There's the O people. Now, to simplify this, it's pretty easy because if your numerator and denominator end in 0, you can just knock those off, and that's the equivalent of dividing both sides by 10. I mean, both numerator and denominator by 10. Okay. And now, fraction-wise, we're going to take it and put it so that's 0.42. Okay. So that's two basic straightforward probabilities. But how can we use this thing? That's the key right there. Sometimes this can save us some work. Sometimes this can save us some work to use the complement rule, especially if we got a lot of data But let's use it now with the probability of not AB. So the probability okay. So I'm going to go ahead and put this just to show you what I'm doing. So that's 1 minus. So what was, I'm sorry, not A, it's probability of AB. There we go. So the probability of not AB is equal to 1 minus the probability of AB. What was the probability of AB? Well, it was 0.032. Oops. So then that's going to be 0.968, as I just showed you on the calculator. Okay. Back to that so you can see. See, 1 minus that gives us 0.968, not 958. Okay. So that's how probability works. Any kind of questions? We'll go over it again in 120. I might just go over it a little bit faster just to see how much we can get through on that. But I like to use these for the OTOs for kind of giving you a little bit more insight. Let's go up here and do this little video. It only takes a few minutes. And then after the video, I'll give you some time to work on this. You got a little thing in there, the valuation 2. You can take it, I think, a few times, get the best score you want. Again, that's going to be a participation grade. All right. So let me do the video thing.
Well, I can't already graded me on it.
What's that?
That evaluation too. The system already graded me on it.
Yeah,
They
there's
didn't give me
something
a chance to
crazy
do it.
about it, but when you actually do it, it fills in the grade. I
Okay.
don't know why it's doing that for certain people. I'm going to make sure that it's not, you're not getting cheated by midterm, when I make sure all the grades are accurate. Okay. But yeah, I
That's the
noticed that it's
second
doing
time and
that.
it did it on me.
Yeah. Like I said, I don't know why it's doing. I was talking to somebody today about it and they say, hey, I noticed, and I'm going to check it out to make sure nothing fishy's happening. But what looks like it's happened before, it was doing it at the beginning of the semester, and they eventually fill in correctly. I just it's never done that before, so I don't know. It must be some kind of a glitch, and
Oh
it's just
yeah,
doing
it
it for
has. It has.
yeah, but it fills in.
Ready to be an e-commerce pioneer?
All right.
Post has step-by-step WordPress onboarding to make creating and running a great.
What's going on here? All right, let's see if this plays. And you can go ahead and work on your assignment after this. Like I said, this is just something to kind of try to explain this concept of law of large numbers.
Decide how much to charge for car insurance. How do casinos set up payout structures to make sure that they make a profit? How does a poker player decide whether or not to fold? How do we efficiently measure the appeal of a political candidate? The answers to these questions are informed by the law of large numbers. The law of large numbers states that as the number of trials or observations increases, the actual or observed probability approaches the theoretical or expected probability. This is assuming the coin is fair, we know that the theoretical probability of flipping heads is 0.5 or 50%. However, that doesn't guarantee that if we flip a coin 10 times, we'll get 5 heads. But we can be confident that as we continue flipping a coin indefinitely, the cumulative proportion of heads flipped should get closer and closer to 50%. So the first flip is tails. So our current proportion is 0 heads out of 1 flip, 0%. The second flip is also tails. So now it's 0 heads out of 2 flips, still 0% heads. Next flip is tails again, 0%. Then heads. Now we have 1 heads out of 4 flips, 25% heads. Flip again and it's heads, 40%. Heads again, and we finally hit our theoretical probability of 50% for the first time. Let's keep going. This graph shows the observed probability approaching the theoretical probability. One common misconception, referred to as the gambler's fallacy, is that if the first 4 flips were tails, you're more likely to get heads on the next flip because the proportion is supposed to even out to 50% heads. This is not the case because each flip of a coin is an independent event. Its outcome is unaffected by all previous events. So if you start out with 4 tails in a row, it's not that you're more likely to get heads, it's just that in the grand scheme of things, 4 tails flips will get averaged with a huge number of flips that are expected to yield an even number of heads and tails, causing the proportion to approach 50% as the number of trials increases. Another version of the law of large numbers explains that the more people from a population that you sample, so the larger your sample size, assuming your sample is free from bias, the closer your sample average will be to the population average. Let's say you have a group of 100 people. Each has some number of dollars in their wallet. If we ask one person how much money she has in her wallet, we'll get our first observation, $49, which might be pretty far from the average of the group. After asking the second person, $29, and averaging that value with the first, we are likely to have a better estimate of the group average. As we continue this process of adding observations and thereby increasing our sample size, we'll generally get better and better estimates of the group's average. So the law of large numbers gives us a compass with which to navigate the randomness around us. Even though we can never predict the outcome of a single coin flip, we can know that over time about half of the flips will be heads. And in general, the principle supports the idea that a well-founded strategy that is followed consistently should win out over time, even though it might result in a few negative events along the way. Thanks for watching. See you next time.
So that's just showing you what probability and how it works. And the rest of the course is going to be based upon probability. Statistics is based upon probability, and of course, probability is probability. So that's why this is crucial to understand this. And they mentioned that about the gambler's fallacy. If somebody, every now and then you'll hear about somebody that's got some kind of a method that they'll use, and they'll go to the casino. And the problem with that is if they've got a winning strategy, if the casino finds out about it, they can kick you out, of course. But it's not that, and it's hard to spot somebody like that because it's not that they don't lose. It's just they find something that shifts the probability in their favor just enough so that over time they won't lose. Whereas, the sad news is the casino's running a business, so their expected value is what we're going to find out later in chapter 10 is always going to be positive, and for the player will be negative. That doesn't mean that you can't win, but it just means that over time the house is going to reap a profit. All right, so go ahead and this is what we did here. So go ahead and work on this now for the rest. And if you got a question, you got about 20 minutes, so I'm gonna be here. So if you got any kind of questions, you can put it in chat or just let me know. All right. You got that? Evaluation 2, and it's in the 020.
Okay.
Not the 120. Like I said, you got several attempts to do it, and it's just a participation grade.